Have you ever wondered how a digital device actually works? As humans, we have a brain to think and different organs that perform different functions. Our eyes help us see, our ears help us hear, our mouth helps us speak. Each organ has a specific role, and together they allow us to perform complex tasks. In a very similar way, a digital device also works using different functional blocks. Instead of a brain, it has processing units like the CPU and GPU. Instead of organs, it has circuits, logic, and memory, each designed to perform a specific function. The field that designs, integrates, and connects all these building blocks inside a single chip is called VLSI. In this video, we'll understand what VLSI is, how it evolved, why it matters today, and how you can start learning VLSI step by step. What is VLSI? VLSI stands for Very Large Scale Integration. In simple terms, VLSI is the process of integrating a very large number of electronic components, such as transistors and logic gates, onto a single silicon chip. Earlier, electronic circuits were built using separate components. If you look at the first generation of computers, they occupied entire rooms. Each function required individual components, long wiring, and consumed a lot of power. As computers became more complex, this approach became inefficient. Large systems were slow, power-hungry, and difficult to scale. This created a clear need. How can we make computers smaller, faster, and more reliable? This need for integration led to small-scale integration, or SSI, where a small number of logic gates were placed on a single chip. As fabrication technology improved, this evolved into medium-scale integration, MSI, and then large-scale integration, LSI. Eventually, this evolution reached very large-scale integration, or VLSI, where millions to billions of transistors are integrated onto a single chip. Modern VLSI chips are manufactured using technology nodes measured in nanometers, such as 28 nanometers, 14 nanometers, 7 nanometers, and even smaller. Today, the industry is moving beyond nanometers into what is often called the angstrom era. When we say nanometers or angstroms, we are talking about extremely small length scales used to describe how small modern chip features are, such as the size of transistors and their critical dimensions. Smaller feature sizes allow more transistors to fit into the same area, which generally improves performance and power efficiency. This continuous scaling is what allows modern chips to deliver massive performance in such small physical sizes. Why VLSI matters today? Because of this level of integration, VLSI completely changed what computers are capable of. Tasks that once required entire rooms of hardware can now be performed inside a single chip, which can easily fit inside your fist. Today, VLSI is at the heart of almost every modern system. From smartphones and laptops, to data centers and cloud computing, to automotive electronics and medical devices. Even technologies like artificial intelligence and machine learning depend heavily on specialized VLSI hardware to run efficiently. You can see the impact of this demand in the real world. For example, the rising prices of RAM are closely linked to the growing demand from data centers. As more services move to the cloud, data centers must store and process massive amounts of data. Workloads such as AI training, large databases, video streaming, and cloud services require huge amounts of memory to operate efficiently. This drives higher demand for RAM, putting pressure on manufacturing and increasing costs. That is why VLSI today is not just about making chips smaller. It is about higher performance, lower power consumption, and better reliability. This makes VLSI a core technology behind almost every digital innovation we use. VLSI is not a single job role. It is an ecosystem made up of multiple subdomains, each responsible for a different stage of building a chip. The first subdomain is RTL design. RTL, or register transfer level, is where the functionality of the chip is designed. Here, engineers define how data moves, how logic behaves, and how the system works cycle by cycle. In simple terms, RTL is where the actual designing of the chip begins, by defining its behavior before it becomes real hardware. Second subdomain is verification or design verification. Once the design is written, it must be verified to ensure it works exactly as intended. Verification focuses on checking correctness and corner cases. This stage is critical because the cost of fixing bugs increases exponentially as we move later in the design flow. A bug found early can be fixed in code. The same bug found after fabrication can require a costly respin, delaying the product by months and costing millions. That is why verification plays such a crucial role in VLSI. Third subdomain is physical design. After verification, the design is converted into a physical silicon layout. This stage focuses on placement, routing, timing, power, and area optimization. Physical design answers the question, how do we build this chip on silicon while meeting performance and power goals? Fourth subdomain is design for testability. Once chips are manufactured, they must be tested at scale. DFT ensures that internal logic can be tested efficiently. Without DFT, mass production of chips would not be practical. Fifth subdomain is analog mixed signal. Analog and mixed signal circuits connect digital logic to real-world signals like voltage, current, and time. Before specializing into any role, there is a common foundation almost every VLSI engineer needs. This includes basic logic gates and Boolean algebra, number systems, flip-flops and registers, finite state machines, timing concepts, Linux, and Python or Perl, commonly used in RTL, verification, physical design, and DFT roles, but is not required for analog mixed signal engineers. Once this foundation is in place, learning advanced topics becomes much easier. Now let's briefly look at where this learning path can take you. This is a career map, not something you need to choose today. For RTL Design Engineer, RTL Concepts and Architecture, Verilog and System Verilog, Simulation and Synthesis, Block-Level Design Thinking. For Verification or DV Engineer, System Verilog in Depth, UVM Methodology, Assertions and Coverage, Lint and CDC Analysis, Waveform Debugging. For Physical Design Engineer, Physical Implementation Flow, Timing Analysis and Closure, Power and Area Optimization. For DFT Engineer, Scan Architectures, Fault Models, Test Pattern Generation. For Analog Mixed Signal Engineer, SPICE, Transistor Level Circuit Design, Noise, Stability and Matching, Analog Layout and Silicon Validation. Everyone starts with the same base. Specialization happens later. We've covered a lot in this video, from what VLSI is, to how it evolved, why it matters today, and what's next. Paths it can open for you. If some parts felt new or overwhelming, that's completely okay. You are not expected to understand everything today. VLSI is a field where clarity comes from building concepts step by step, not all at once. On this channel, bit by bit, we'll start from the fundamentals, connect concepts as we move forward, and slowly build a strong understanding of VLSI. In the next video, we'll begin with the fundamentals of VLSI and digital design, and then move gradually toward real-world design and verification topics. Till then, stay curious and learn tech bit by bit.